All right, so today we're going to talk about taking the atomic model to the next level. Here you can see Bohr's model of the atom, which is the one we sort of left with when we talked about emission spectra, which is what you see over here on the right, the energies of electrons given off as they fall back down to their ground state from an excited state, like in the flame test. And then, the absorbance spectra would be just the opposite of these. The energy absorbed, or the energy of existing light absorbed by these same atoms as electrons are being elevated to higher excited states. So the problem with the Bohr model is it only worked for basically one electron. So hydrogen, you could explain the structure of the hydrogen atom because it only gave off the certain limited number of different frequencies of light. And so it made sense to say that electrons were, jumping from 1 up to 2 or from 1 up to 3, falling back down, giving off these frequencies of light. But it actually turns out that when we get into larger atoms like sodium, even helium, which only has, normally has 2 electrons, or any of these larger elements, we start getting a huge number of different wavelengths that can be given off. And especially when we start to add them all together and we look at all the different amounts of energy that can be given off. There are subtle little differences between these energies that you see here for neon, through the red and orange part of the spectrum. So what's accounting for all of that? There must be more than just the first, second, third, fourth, fifth energy level, and so on, if we're getting all of these dozens and even hundreds of different energies being given off by atoms as their electrons are excited. So there must be more to it. So we can say that the Bohr model simply didn't account for the huge number of different electron energies which correspond to all these different bands of light. So one of the people that came along to explain this was Werner Heisenberg. And essentially what he said was, for really small particles, it's impossible to know both the position and the momentum of a really small particle like an electron. The more you know about its position, the less we know about its momentum. And so the way you can think of this is just essentially electrons are just sort of showing up here and there. We can't really track their motion, so we're not going to think of it as a circular motion like the planets around the sun. We're just going to sort of think of them as these mysterious, very small particles that are just sort of popping up here and then there and then over here. And so instead of a very fixed orbit, that's the way we want to think of electrons. So basically, in order to measure the momentum of an electron, or basically the velocity, how fast it's going, you have to change its momentum. You have to give it some. You have to hit it with some kind of energy, causing it to move, and therefore changing both its position and its momentum. So it's very difficult to measure both at the same time. For larger objects, it's easy. You can know the mass and velocity of, a car as well as its position at the same time. But for really, really small, fast-moving objects like electrons, it's impossible to know them both with great certainty. As one goes up, the other goes down. So the more I know about the position of the electron, the less I know about how fast it's moving, in space. So what you see there is a graph of probability along the y-axis versus distance, essentially distance out from the nucleus of an electron. And for this particular one, I believe this is just describing the first electron in hydrogen. So if you look here, it gives this distance in nanometers. And so what it's telling us is that not necessarily that hydrogen's one electron is this distance out from the nucleus, again the nucleus being at a distance of 0, but we're just we're most likely to find the electron at this distance represented by the dotted line. So in this case 0.0529 nanometers from the nucleus. So it's just telling us where we're most likely to find it. So again, if we think of an electron as just sort of, showing up here, 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 and here at various times, it creates this image that's very fuzzy, very sort of cloudy, very vague about the position of that electron, because we don't know the position of the electron. We just know where we're most likely to find it. And that's what this graph is describing. So could we have an electron this close to the nucleus? Absolutely. Could we have it way out here? Absolutely. But the probability is really low. And one interesting thing here is you'll notice that it never really, it kind of has this asymptote shape to it, where it never really reaches zero, which means the electron could be, a meter away from the nucleus. Now, is that likely? No, but it's possible. And so that's the Heisenberg uncertainty principle. What you end up with is an image of the atom and its electrons that kind of looks like these two images. These are basically just probability scatters or graphs of where we're most likely to see the electron within an atom. So if you, again, just keep it simple, imagine a hydrogen atom. It has one electron. Where is that electron if you were to snap 1,000 pictures and lay them on top of each other? Well, you would get that electron sometimes showing up way out here, most of the time showing up in much, much closer to the nucleus. But you can see here it creates just sort of a cloud of probability of finding the electron. And then this picture over here on the right is just, kind of the same idea. Okay. So, if we talk for just a second about orbitals, or go back, to energy levels rather. Energy levels don't fully describe, we said that when we looked at the first picture, energy levels don't really describe all of the different energies that electrons can have. They can have a lot of different energies, and I'm going to click back to my first picture here. You can see the subtle little differences between the energies given off by neon atoms, for example, as they're heated. Well, the way that physicists of the early part of the 20th century basically thought of this was that not only can we not really say for sure that where the electron is at any point in time, it's not always just a simple spherical area around the nucleus where we're most likely to find the electron. We have these things called sublevels. And you can think of sublevels as being sort of like rooms within a building. You have floors, but most buildings, unless it's just like a warehouse type building, most buildings have, within floors, they have rooms. You have so many rooms on the first floor, the second floor, and so forth. Well, atoms' energy levels can be thought of as floors with sub-energy levels or sublevels within those floors. And the simplest of those is in fact a spherical shape, kind of like what we just saw with the hydrogen atom. And so our first sublevel, or you could think of it as a sub-energy level, is the S-shaped orbital. And it just means, you can think of it as meaning a sphere, basically. It's not really what it stands for, but basically it's just a sphere. So if I have a hydrogen atom with just one electron, that one electron is going to be in the first energy level, unless it's excited, and it's going to be in this sort of spherical cloud around the nucleus. This is just the area where we're most likely to find that hydrogen electron. So there's one of these per energy level, and each orbital, regardless of its shape, we're starting out with the simplest one, it's just a sphere, but regardless of its shape, each orbital can hold each sublevel or orbital can hold 2 electrons. So therefore, for every energy level, the first, second, third, fourth, fifth, each of them can have one of these spherical sublevels, and that sublevel, no matter how small or large, can only hold 2 electrons. So in each energy level, we have a spherical sublevel, and that spherical sublevel can hold 2 electrons. Okay, so the next one after S is called P. And P is just basically twice as complex as S. So it's these sort of double-lobed, peanut-shaped orbitals around the nucleus that, just like the S, can each hold 2 electrons. And again, this is just an area where we're most likely to find the electrons. And by the way, the first energy level doesn't have P-shaped orbitals. These don't show up until energy level number 2. So starting with the second energy level, we can have 2 electrons in each of 3 different P-shaped orbitals. So there are 3 different orientations. Each of those orientations is its own orbital and can hold 2 electrons. So that means we can have 6 electrons per energy level in the P shape, except of course for energy level 1, which doesn't have any P-shaped orbitals. So the thing you have to remember is we've separated these out into 3 pictures so that you can see them a little bit clearer. But in the atom, you would have all 3 of these orbitals, like, intermingling with each other, with the origin, with basically 0, 0 being the nucleus. But if you can imagine those 3 pictures sort of overlapping, so you have the 2 lobes going along the x-axis, along the y, and then also along the z, kind of coming out towards you. The next one up, and by the way, you should try to draw these. Basically, the only thing you really need to know is that they're twice as complex as the previous one. So the D is basically twice as complex as the P. But it's the same concept. It's just kind of funkier looking. It's I always remember D for daisy, because you can kind of think of these as like flower petals, except for this last weird looking guy with the sort of north-south axis and then the hula hoop around the middle. But again, remember, these are just areas where we're most likely to find electrons within the atom. So the d orbital doesn't come in until the 3rd energy level. So the 1st and 2nd energy levels of an atom don't have these. It's not until we get to larger atoms that need to occupy the 3rd, 4th, 5th energy levels where we actually have d-shaped orbitals. And again, just a region where we're most likely to find electrons. I don't want you to think of these as the path that the electron is taking. So some people look at this and they go, oh, okay, so that means, we have these 4 lobes like a 4-leaf clover, so that means the electron is kind of doing like a 4-way figure 8 here. And that's not what's happening. This is just, if we were to snap a picture of the electrons that are in D-shaped orbitals, let's say in the 3rd energy level, these cloudy areas are simply where we're most likely to find them. Okay? Now there are 5 of them that can fit per energy level, and again you want to think of them as just sort of overlapping one another. And since there are 5 of them per energy level, that means we can have 10 electrons in D-shaped orbitals per energy level. The last one I'll show you is super funky and weird looking, and it is F. And this is really hard to draw. You can try. I would encourage you to try to do, I don't know, maybe like this first one. Basically, it's just like 4 lobes facing up and 4 lobes facing down. That doesn't really account for all 7 of them that you'll have, but you get the idea that it's just twice as complex as D, and that's really all I want you to know. Now, as they get more and more complex, you'll notice that we have more of them that can occupy an energy level. The F doesn't show up until the 4th energy level. We'll get into all that a little bit more in class, but so we can have 7 of these per energy level, starting with energy level number 4, and that means since each one of them is its own orbital and can hold 2 electrons, 7 times 2 is 14. So we can actually have 14 of these per energy level. We're going to get into how exactly, like the order that they fill in class next time, but for right now I just want you to sort of have some exposure to the idea of these orbitals just being areas where we're most likely to find electrons, and then what the shapes are and how many electrons can fit in each one. So hopefully you wrote down the notes. Watch the video again if you need to, and come to class with lots of questions next time. Thanks.